Respiratory dynamics. The ventilation is the volume of air breathed in per minute and can be calculated through multiplying breath rate and tidal volume. This means ventilation is directly proportional to these, and therefore if one increases, so will the ventilation. This can be seen as if more breaths are taken in a minute, clearly a higher volume of air will be inhaled as long as the tidal volume stays the same. Values at rest for this are usually 6 litres for ventilation, 12 breaths for breath rate, and 500 millilitres for tidal volume, as can be seen in the PowerPoint. Also in the PowerPoint, we can see how the breathing rate is affected during exercise, such as the multi-stage fitness test, as it increases as a steady rate after every 2 levels. This therefore has a direct effect on ventilation, as it will increase because the breath rate is multiplied with another number to get the ventilation. Although the average numbers for tidal volume, breath rate and ventilation are shown above, these will change during exercise, which can clearly be seen in a spirometer trace, as this shows the different lung volumes throughout the exercise, suggesting that as the exercise increases with intensity, the lung breaths will become more deeper, as more space has been created in the lungs, allowing for a higher tidal volume. It also shows that the breathing becomes more quicker, increasing the breath rate, which can be seen as the gap between the most recent breath. Forced breathing mechanics and control. Respiration slightly changes during exercise or sporting activities as both inspiration and expiration becomes active, despite one being passive during respiration at rest. For example, during inspiration, the diaphragm and intercostal muscles act similarly to before, as they both contract as an impulse has been sent from the motor cortex down the spinal cord, stimulating this, with the intercostal muscles moving up and out and the diaphragm down into a straight line. However, the first difference comes with the accessory muscles, as these also contract, allowing for more space in the thorax. The scalene muscle elevates the ribs, the pectoralis minor muscles pulls the ribs out, and the SCM elevates the sternum. If this is increased to maximum extent, the Herring-Burr reflex is forced into use as a stretch receptor to send a signal to the medulla oblongata through the vagus nerve to stop the muscles from contracting out and increasing the cavity as it has reached its maximum point. Due to this, there is now more space in the thoracic cavity, and therefore a higher volume of air is enabled to enter. And because of Boyle's law showing that pressure is inversely proportional to this, it decreases by a higher amount, much lower than the atmospheric pressure. Finally, as the pressure is much lower, a steep difference is created, and as air moves from high to low volume, high volume of air enters the lungs that can be distributed to the muscles. It's a very similar process with expiration, as the volume of air leaving also needs to be a lot due to the high volume of air that was initially inhaled. Early in the process it differs with expiration at rest, as not only do the diaphragm and external intercostal muscles relax, but the internal intercostal muscles contract to depress the ribs further, decreasing the volume and changing it to an active process as a contraction has occurred. This is achieved through the Respiratory Control Center, VRG, as it is able to adjust breathing rate during exercise through sending impulses to the apneustic center, causing the muscles to contract inwards, making it an active process. As the volume decreases dramatically, the pressure does the inverse and increases dramatically, making it much higher than the atmospheric pressure, forcing a high volume of air to leave the lungs once again due to Boyle's law. The Valsalva maneuver. The Valsalva maneuver is a particular way of breathing that can be performed during exercise to help the body with physical exertion by increasing the pressure in the thorax, which causes the surrounding muscles to contract and ultimately increasing the effectiveness of activity as it enhances performance. It does this through the body attempting to breathe out, but instead being blocked by the epiglottis, causing the torso to become stronger. It also reduces the amount of blood being pumped out from the heart, but speeding up the heart rate, causing the blood pressure to attempt to increase, which is maintained through vasoconstriction. This technique is highly effective during exercise like weightlifting, for example, as it stabilizes the body as the torso becomes stronger, which supports the vertebral column, similarly to a weight belt, allowing the lifter to lift the weight above their body. While looking into ventilation and how it is increased, we carried out 2 tests to measure the breathing rate as exercise increased. At rest, both breathing rates were at 13 beats per minute, which is normal for a healthy human being, and both are passive respiration. However, it becomes active during the test. Both tests saw an anticipatory rise just before the test began, which could mean the students were nervous. However, it was likely the body was preparing for exercise, and therefore the brain was sending impulses down to increase the breathing rate before the test began. As you can see in the multi-stage fitness test, as the levels increase, so did the breathing rate. This can be interpreted that due to the intensity of the exercise increasing, the respiratory system had to counter this through producing a higher ventilation, and therefore a higher breathing rate, as the two are proportional. Although we have no data for this, it is also likely the tidal volume increased in order to also raise the ventilation. It is also important to look at the rate in which the breathing rate increased, because as shown on the graph, the increase was gradual, suggesting the system was working at a steady rate, and this is because there was no dramatic increase in the intensity of the exercise in each stage. The breathing rate was at its highest point post-test, which was just after the test was finished, and is justifiable, as this was after the highest intensity stage. At this point, we can also suggest that the ventilation was at its highest, as after the exercise the breathing rate would begin to slow down to its natural rate, and therefore decrease the ventilation. This is similar with the Wingate test, as in the short time that the test progressed, the breathing rate increased at a quicker rate. This is due to the intensity being much higher. The breathing rate has to increase to allow for a quick high ventilation. Sports application analysis. Active respiration is used in almost any sport, as the body needs to take in oxygen and remove carbon dioxide as more oxygen is lost in exercise. For this to occur, the volume of air breathed per minute must increase as the game progresses, and therefore relies on breathing rate and tidal volume to increase. For example, in rugby, it is likely a player will begin the match with a breathing rate slightly higher than at rest due to the anticipatory rise, which would slowly rise as the game progresses, as the muscles may begin to tire and therefore desire more oxygen. However, different factors could slightly affect this, like being winded, for example, which is common in a contact sport, which may lower the breathing rate. However, the body also attempts to stop being winded in this type of game through the Valsalva manoeuvre, that a player may perform in a scrum or before a tackle, as it will assist in bracing them for impact, as it strengthens the torso through the epiglottis, blocking the air from leaving the body. Overall, throughout a match, it is likely the heart rate and tidal volume will rise as the body undergoes active respiration, therefore increasing the ventilation.